From Kagool again. I want to show you an interesting feature that you can achieve with mixed reality models. Okay, and that's called subassembly decomposition, and we'll just briefly touch upon it on why it's so important, but I'll just show you right now what it means visually. Okay, so subassembly decomposition is the capability to take a digital model and be able to separate it into its subassembly components. There is lots of useful applications to this. I mean, if you look at the model which we've pretty closely, the physical model which we've pretty closely replicated in the background, it's pretty difficult to take that to bits and work out, troubleshoot issues within certain areas of it. And I think any engineer will know that a big machine like that was actually be made up of 20 or 30 kind of big chunks of subassembly equipment which together make up the whole. So in the same way in the last video we had those little diamonds on the top, we can see them bouncing around. Yeah. So what we can do now is we can look at the subassembly in isolation, and it makes it much easier to investigate when you've got quite a complicated integrated machine like this. So if we just click on that diamond, so the IoT telemetry that's been pumped out from the physical machine is pumped into Microsoft Azure, and then we can retrieve that information directly in real time from the digital model. And this has been updated, this model, so you can see there's lots of moving parts. We can zoom in to see those moving parts. Yeah. Okay, in. There's the conveyor belt. Oopsie daisy. So why is this important? So, well, we can zoom in to the interior of the subassembly without actually having to take the thing to bits. So what's useful there is that from a downtime perspective, let's reset it. Yeah, so there's no downtime for the investigation, providing you've got all the IoT information being sucked into the Azure platform. You can decompose the model as much as you like and investigate and perform the necessary incident management and diagnosis. So there's no downtime. It reduces the downtime, which is good when you've got big, expensive pieces of equipment. What else? Safety reasons. So you've not actually got a human being climbing into the interior of all these moving parts to see what's going on. So all you're doing is you're using the ability to investigate the real life simulation of the equipment with all the telemetry being pumped out, and you're not actually having to send a human being inside. Okay, so there's loads of applications here, and it's great graphics as well, isn't it? So there's about 3,000, 3 or 4,000 parts in this model. A few people asked after the last video, what's the point of having a digital twin? There's some good examples. So the NASA actually, so twins of large physical equipment have been around for a long time. If you look at NASA, so NASA had when NASA was running the Apollo missions, they were creating physical twins of the lunar modules and all the equipment that was being sent into space. And why did they do that? Because it's very difficult to diagnose issues once you've sent the equipment into space and you collected the telemetry. I mean, they were doing that through radio back down to Earth, but they weren't able to, what do you do with it? You're looking at it on a black and green screen as it was back then. So what they were doing is they were pumping that information into physical equivalents of the physical twins of the model that was in space or on the moon. Now, and why did they do that? Well, that helped with diagnosis. It helped with change management when they wanted to make changes to the equipment. And so it's been going around for a very long time now. So the concept of a twin is not unusual. What is unusual now is the technology enables the digitization of these models to such an accurate degree. But the model is one thing. I mean, CAD models have been going on for a long time, but it's the IoT capability of augmenting the model with the actual telemetry in real time from the actual physical machine. That's what's new, and that's what's really helping. I mean, the technology's here now. It wasn't there a number of years ago, especially for real time digital twinning. Okay. Now all this technology is powered by we've got a combination of SAP data in here. We've got IoT data, so we can pull any of the SAP information back up. Here it's on the middle one. Where are we? Where's the SAP data? And you can tell that the geospatial alignment of all of the parts is consistent as I move around. Apologies, I've got shaky hands. I'm on an iPad and not a phone, which could have had a stabilizer on it. So okay, so if we click on the blue one in the middle, there we go. So that's just an example of pulling back some SAP data into the model via Microsoft Azure. Again, this is real-time SAP data which is ingested into Azure Data Lake. Okay. It's just absolutely amazing technology, this. Next week we are moving this model into a new preview service provided by Microsoft, which is Microsoft Azure Digital Twin, whereby the entire thing for the IoT capability, the actual Unity model itself, all of that gets saved into a new Azure service, Azure Digital Twin. So that's going to be quite exciting. So we're looking forward to doing that. So that should take a couple of weeks to integrate, and then we'll probably do another demonstration to show you how great those capabilities are. Initial impressions looks like it's really going to help automate and integrate and industrialize this kind of capability of drawing all the data together. So at the moment we're using we've got SAP IoT data ingested using Velocity, which is our ingestion tool, into Azure, and we're using the various different IoT and standard cloud data services to present that or to integrate the data and present it through mixed reality simulation. Okay, thank you for your time. Any questions? info@kagool.com. Thank you. Bye.